Good day, everyone. Welcome to That Friendly Writer's Statistics and Data Analysis tutorial videos for TVL students. This is my YouTube channel where you can watch lots of statistics and data analysis videos. Today, we'll learn about the central limit theorem. This is just an introduction, so there will be no calculations yet in this video. Alright, let's get started. If a population has a very large size, like thousands or even millions, how do we study its distribution? Random variables such as heights, baby weights, blood pressure, IQ, and student exam scores are not a problem because these are naturally normally distributed over a large population. This is good because we can easily study its true mean mu. However, there are also some random variables that cannot be immediately considered normal, such as monthly income, because this is a skewed distribution. Also, any discrete random variable, such as number of children in the family and number of customers in a restaurant, cannot be considered normal at all. Because remember, a normal random variable has to be continuous. If this is the case, how can we determine the true mean mu? This is where we use the central limit theorem. This is arguably the most important theorem discovered in statistical inference. What does this tell us? If we have an original population that is already considered normal, then the sampling distribution of the sample means will become normally distributed, even for low sample sizes. If our original population begins deviating away from a normal distribution, then we may require a larger sample size to do this. In this illustration, our population is now only an approximation. Hence, we may require a slightly larger sample size. But if we have a distribution that seems to be very different from a normal distribution, like this left skewed population, well, we may require a truly larger sample size to achieve this assumption of normality. But the point is this: when we take a random sample from any kind of population, whether normal, skewed, or no pattern at all, if we get the sample mean, it becomes a random variable with a normal distribution, on the condition that we have a sufficiently large sample size. How big should the sample be? Sources say it should be a minimum of 30. Remember that this 30 here is only a suggestion, not a magic number to follow. This is the central limit theorem. So, how can we make use of this? If we have an unknown population whose original mean is 4.5, what happens if we try to get larger and larger samples from this population? It approaches normality. A sample mean x bar that comes from a large size sample becomes a point on a much clearer normal distribution. And the good thing is, the original mean mu is the same as the mean of the sampling distribution. In this example, both are 4.5. There we go, the central limit theorem in action. For our practice, let us determine whether a sample size taken is enough to achieve normality of the sample mean. For this normal distribution, is it enough to get a sample of n equals 12 only? The answer is yes, it's enough, sufficient, since we already have an almost normal distribution. A small sample size is enough to achieve normality of the sample mean. How about the second one? An approximately normal distribution, and we are to take n equals 24. This is probably enough, especially that the data is already approximately normal. Next is a bimodal distribution. This is clearly not normal because there are two peaks. Is getting a sample of size 67 enough? In my assessment, I don't agree yet that 67 may be enough, since it's going to take quite a while for the means of a bimodal data to become normally distributed. I guess maybe 100 will do? We can only guess for now. In fact, there is also a possibility that I may be wrong with my assessment. A left skewed distribution like this, for me, is not enough or sufficient to just use 31. I suggest using sample size of 50 for this kind of population. Now, this is tricky. You might say this is already normal, but this is a discrete random variable population. Using only n equals 10 sample size may not be sufficient for a discrete case. Especially this one, taking only 4 for a discrete population, this is clearly not sufficient at all. It's going to require a larger sample size. How about another discrete distribution, but using a sample size of 37? I guess to me this is enough, and hopefully I am correct in my assessment. For a weird looking random distribution like this, getting a sample size of 29 is definitely not enough. We have to take a larger sample. What if we don't know the distribution at all and look for a sample size of n equals 17? Definitely that's too low to achieve normality for the sample means, especially for a population that we don't even know. How about if we do exactly 30? Remember that 30 is not a magic number, it is only a recommendation. Let's not push our luck with this. We don't know the distribution, right? Then aim for a larger sample size if we want to assure normality. The bottom line is, if we are unsure about a population, the rule of thumb is to get a larger sample size. As they say, it is better safe than sorry. The larger the sample size, the better we can estimate the mean mu. Alright, this concludes our video for today. Hope you learned something new. Have a friendly day!